So now in this video, we'll be looking at the concept of the Kepler laws of planetary motion. So what are Kepler's laws of planetary motion? Kepler, he analyzed the astronomical data based on Copernicus theory. And due to this, he formulated some laws of Kepler, which were later called Kepler laws of planetary motion. So let's first study about the Kepler's first law. Kepler first law, which is also called the law of orbits. It's also called law of orbits. And according to Kepler first law, it says that each planet revolves around the sun, revolve around the sun uh, in an elliptical orbit. In an elliptical orbit, and the sun is situated. The sun is, situated at one foci of the ellipse. At one foci of the ellipse. So this is Kepler's first law, which is also called the law of orbits. Because you know that, like if we draw an ellipse has two axes. This is one is called major axis, and this is called the minor axis. Okay. And ellipse has two focus. We can have two focus, F1 and F2. So that's why the plural form is foci. So basically, this theory is saying that the planets are revolving in an elliptical orbit. We have major axis and minor axis, and the sun is suppose located here at one of the foci. So this is our sun, right? So this is our major axis, and the shorter one is our minor axis. O is the center, and there are two positions. So this planet is revolving. This is the planet, which is revolving in this elliptical orbit. Okay. And there are two positions. So this is the position A of the planet when it is away from the sun, which is called aphelion position. And there is another position represented by P when the planet is closer to the sun. And this position is called perihelion position. Perihelion. Okay. And position A is called the aphelion position. Aphelion. So you can say that this PO, so here you can say that this PO, which is equal to OA, which is presented by small a. The small a is called the semi-major axis of the ellipse. This is the semi-major axis of the ellipse. Okay. So now here we can define the eccentricity of the ellipse. So let us look at the concept of eccentricity. So let me again draw that diagram. So this is the diagram of the ellipse. We have drawn the major axis, we have drawn minor axis. This is the position of the sun. This is the aphelion position. We have a perihelion position. Who is the center? The eccentricity is defined as the ratio of the distance of one focus from the center of the ellipse, which is suppose SO, divided by OP. OP here is the semi-major axis. Half of the major axis is the semi-major axis. So eccentricity is defined as the ratio of the distance of one of the focus from the center of the ellipse to the distance of the semi-major axis of the ellipse. SO divided by OP. Or we can write it as SO divided by, now what is OP? OP is represented by small a. So from here we can conclude that SO is equal to E times A. SO is equal to E times A. Okay. Now if we look at like, let me draw another diagram. So again, this is the ellipse. This is the major axis. This is the minor axis. O is the center. This is the sun located at point S. Aphelion position, perihelion position. So the semi-major axis here is marked by A. A is the semi-major axis. RA is the distance of this point A from sun, and RP is the distance of point P from the sun. RP is the distance of point P from the sun. So you can easily see that our SP, so here SP is equal to RP. SP is equal to RP. And SA is equal to RA. So we can easily conclude that SP, so this distance SP will be equal to how much? It will be equal to OP minus OS. So OP minus OS, right? OP or PO is equal to, OP is equal to what is, this is A, semi-major axis. So A minus OS means SO, which is EA. So A minus EA. This is SP. Okay, or we can also say that SP is equal to, so we can take A common. If we take A common, it becomes 1 minus E. So A into 1 minus E. So SP is equal to A into 1 minus E. Okay. And if we look at SA, if we look at SA is equal to OA plus OS. SA is equal to OA plus OS. Now, what is OA? OA again is semi-major axis, that is A, plus OS is EA, A plus EA. right? So if I take out A common from here, so we have A into 1 plus E. So SA is equal to 1 plus E and SP is equal to 1 minus E. These are the two important conclusions I have drawn from here. So what I'm going to do is that I'm going to put these two values in this ratio of E. So we know that, or what we can do is, if I look at the ratio of SA divided by SP. So what is SA divided by SP? So SA was the perihelion distance RA divided by, so this was the aphelion distance and SP was the perihelion distance. So RA divided by RP, right? Now our RA was equal to, if you look at this slide, so RA was equal to A into 1 plus E, that is equal to SA, that is equal to A into 1 plus E, and RP, which is equal to SP, is equal to A into 1 minus E. So I'll put these two values here. So RA divided by RP. So I'm going to put RA as A into 1 plus E divided by RP. RP is A into 1 minus E. So A gets cancelled in numerator and denominator. So what we have now is 1 plus E divided by 1 minus E. So we have SA divided by SP is equal to 1 plus E divided by 1 minus. Now for ellipse, the value of E is less than 1. For ellipse, value of eccentricity is always less than 1. And for circle, the value of E is equal to 0. Because, in circles, that focus S is coinciding with the center root. So that's why the eccentricity is taken as 0. Because for circle, the two foci, they are merging into one. And the semi-major axis here becomes the radius of the circle. Okay. So also, we can easily conclude that if we look at the length of the semi-major axis, A will be equal to RA plus RP divided by 2, the length of semi-major axis. And the eccentricity of the orbit is equal to RA minus RP divided by RA plus RP. You can also conclude this relation. A is equal to RA plus RP divided by 2. Okay. And suppose if there is a planet and we say that let capital R here represents the distance of planet from sun. And suppose that planet is revolving with angular velocity omega. So omega here represents the angular velocity of planet. then the area which is swept per unit time by the planet is given by 1 by 2 r square into omega. Okay. And if I multiply and divide this equation by m, what we get is m r square omega divided by 2m. And you know that mr square is called the angular momentum of the planet. So angular momentum is defined as the moment of momentum. So linear momentum multiplied by perpendicular distance. Right? So this whole quantity mr square into omega is also called angular momentum. Mr square is the moment of inertia of the planet and omega is angular velocity. We have one relation, angular momentum, one more relation. Angular momentum L is equal to I omega, where I is the moment of inertia. And the moment of inertia of this planet is equal to mr square. So the area swept per unit time can also be written as L divided by 2n. Where this, so mr square omega, which is equal to, we can write it as m into r mr square omega. It can be written as m into r omega multiplied by r, right? And r omega is equal to v. So this is equal to mv multiplied by r. mv multiplied by r. mv is the linear momentum multiplied by r perpendicular distance. So this will be called the angular momentum of the planet around the sun. Okay. So basically, when the planet is revolving around the sun, since the area swept per unit time is same, so the angular momentum here is conserved. That is a conservation, an example of conservation of angular momentum. Okay. So now we'll be looking at the second law of Kepler, Kepler's second law. Kepler's second law, which is also called the law of areas. Okay. It is also called law of areas. And according to this law, it says that the line joining a planet to the sun sweeps out equal areas in equal intervals of time. The line joining a planet to the sun sweeps out equal areas in equal interval of time. That is the, or we can say that the aerial velocity of the planet the aerial velocity of the planet around the sun is constant. Aerial velocity of the planet around the sun is constant. So let us understand this Kepler law of Kepler's second law or law of areas. So again, we consider our planet which is revolving around the sun in an elliptical orbit. And I'm drawing here the major axis and also the minor axis. Okay. So the sun is located at one of the foci. So S is the position of the sun, right? So RA represents the perihelion distance, and here RP represents the RA represents the aphelion distance, and RP represents the perihelion distance. A and P are the positions, perihelion position and aphelion position and perihelion position. Now suppose the sun is that VA is the velocity of the planet when it is at aphelion position, and VP represents the velocity of the planet when it is at the perihelion position. Now suppose the sun is present, the planet is present at position P1. Now let me mark the position P1. The planet moves from the position P1 to position P2 in time t seconds. Okay. And it also, when it is away from the sun, and when it is closer to the sun, suppose the same planet moves from position P3 to a position P4 in same time t seconds. So here the area swept when it is at position P1 to P2, the area swept by the planet is SP1 P2. This area SP1 P2. And when it is closer to the sun, the area swept is SP3 P4. Area swept is SP3 P4. Okay. So what we are saying is that the area which is swept by the planet will be same. That means this area P1 SP2 will be equal to the area P3 SP4. So these two areas will be same. But because you can see that SP1 here is more than SP3, greater than SP3, as SP1 is greater than SP3. So this implies that so when the distance increases, when the radius increases, the length of the arc will reduce so that the area can be kept constant. The length of the arc will reduce. So that means P1, P2 here will be less than P3, P4. Okay. Or you can say that if I divide both these equations by T, so P1, P2 divided by T will be less than P3, P4 divided by T. So what is P1, P2 by T? P1, P2 by T represents the linear speed of the planet at position P1. And P3, P4 by T represents the linear speed of the planet when it is at position P3. So you can say that the linear position of the planet at position P1 will be less than the linear speed of the planet when it is at position P3. So from this, we can conclude that the linear speed of the planet when it is closer to the sun will be more than the linear speed of the planet when it is away from the sun. So the linear speed is going to vary. Okay. See, the law of areas or Kepler's second law is based on the principle of a law of conservation of angular momentum. It is based on law of conservation of angular momentum. So according to this law, the angular momentum of the planet will remain same whether it is at aphelion position or perihelion position. The angular momentum of the planet when it is at perihelion position is equal to linear momentum, that is m vp multiplied by distance, that is rp, will be equal to the angular momentum of the planet when it is at aphelion position, which is mva multiplied by ra. Okay. Or we can say that because the mass of the planet will remain same, so you can say that vp divided by va will be equal to ra divided by rp. You can say that velocity is inversely proportional to the distance. Okay. So the important thing here is that the Kepler's second law is based on the principle of conservation of angular momentum, right? So now we are going to look at the Kepler third law of planetary motion. Okay. So my dear students, now we are going to look at the Kepler third law of planetary motion, which is also called Kepler law of periods. Okay, so let's look at Kepler third law, also called law of periods. So first of all, let us look at the definition of this law, because Kepler was observing all the planets, they were revolving around the sun. Some of them were closer to the sun, some of them were away from the sun. They were, revolving with different times. But he found that, like when the planets were revolving, the distance were changing, the time were changing, but there was a relationship between the time and the distance. He found that the square of the time period of revolution of all the planets is found to be directly proportional to the cube of the semi-major axis of the elliptical orbit. Okay. So he found this, that the square of the time period of revolution of the planet is found to be directly proportional to the cube of the semi-major axis of the elliptical orbit. So this is our Kepler third law. And this law is one thing, this law is very important from the numerical point of view, because a lot of numericals are asked from this law. And the greatest remarkable thing about Kepler law of planetary motion, especially this law, is that not only the planets, but the satellites which are revolving around any planet, they also, they also obey this Kepler third law. Even the artificial satellites that we are launching even today, they will still obey this Kepler third law of planetary motion. A lot of planets were discovered after this Kepler third law came into existence. And they were also found to obey this relationship. So this was the remarkable thing about Kepler predictions. They were so precise. And also, we can deduce this Kepler third law also. So let us look at the concept of this deduction of Kepler's third law. Deduction of Kepler's third law. How we can deduce it. So let us consider that there is a planet, which is revolving around the sun. That small m represents the mass of planet. Which is revolving around the sun. So capital M represents the mass of sun. Okay. And suppose it is revolving in a circular orbit. So let small r represents the radius of circular orbit in which the planet is revolving. It has some angular velocity. So omega represents the angular velocity of the planet. It represents the angular velocity of the planet, right? And let capital T represents the time period of evolution of the planet. Now we know that there will be a gravitational force of attraction between the planet and the sun, and this gravitational force will provide the necessary centripetal force. So the gravitational force between the planet and the sun is G capital M small m divided by r square. Is providing the necessary centripetal force. So centripetal force is also given by the formula mr omega square. Okay. Now, as you know that omega is equal to 2 pi by capital T. So we can write this as G capital M small m divided by r square is equal to mr into. So omega is 2 pi by capital T. So if I square it, what I get is 4 pi square divided by T square. 4 pi square divided by T square. Right? Or we can say that T square is equal to 4 pi square divided by G capital M. Just I am rearranging the terms multiplied by R cube. Okay. Now, since this 4 pi square by Gm is constant, this whole quantity is constant. So you can easily see that this T square will be directly proportional to R cube. So here I have assumed that the planet is revolving in a circular orbit, but this result holds good even for elliptical orbits, provided this small r, this r is, we can replace this r with a, that is our semi-major axis of the ellipse. Okay. So this is how we can deduce the Kepler third law of planetary motion. So let's solve one problem based on this Kepler's third law of planetary motion also. Okay. So let me go to the next page. So here is one example, illustrative example. It says that the time period of Jupiter is given as 11.6 year. The question says that how far is Jupiter from the sun? So we have to calculate the distance of Jupiter from the sun. So this we have to calculate. It is given that the distance of Earth from the sun, is equal to 1.5 into 10 raised to the power 11 meters. So this distance is given. And because they have given Earth, so we know that the time period of Earth we already know is equal to 1 year. So this we already know. So this is a question based on Kepler third law, which says that T square is directly proportional to R cube. So here one time and one distance, that is distance of Earth and time period of Earth, is known to us. Time period of Jupiter is also known and distance of Jupiter is required to be found. Now, since T square is directly proportional to R cube, so if I take a ratio of the time period of Jupiter to the time period of Earth, I can say that Tj square divided by Te square will be equal to Rj cube divided by Re cube, Rj cube divided by Re cube. Okay, which implies that Rj divided by Re will be equal to Tj divided by Te raised to the power 2 by 3. Or you can say that the distance of Jupiter will be equal to Re, distance of Earth, into Tj by Te raised to the power 2 by 3. Okay, so the distance, so now let us put the values over here. So Rj will be equal to, so what is the value of Re? Re is 1.5 into 10 raised to the power 11 multiplied by Tj. So Tj is 11.6 divided by 1 raised to the power 2 by 3. So that will be equal to, when you calculate it, you get 7.68 into 10 raised to the power 11 meters. Okay. 7.68 into 10 raised to the power 11 meters. So this is the answer we are getting over here. Okay. So this is the question based on Kepler third law.